Hello friends, so welcome back. This is the second lecture. Um, I was talking about Fourier series and transforms, Fourier representations, and the basic idea in all of this is that given a signal, I would like to expand it in terms of some basic units, right? Some basic building blocks, and Fourier representations typically use sinusoids, complex sinusoids as complex exponentials as the typical building blocks. So, given a signal f of x, right? So, can I expand it in terms of some building blocks e to the power of I and x by L? So, x is it's still a function of x, right? F of x is also a function of x. This is also a function of x, and so we are typically going to be dealing with expansions of that type and create new signals. And so that is the basic idea, as I said, of what Fourier proposed. And therefore, there are, depending on what kind of signals I'm dealing with, I can have different kinds of Fourier representations, right? So one of the typical things that we do is what is called the continuous time periodic signals. So f of x here is assumed to be continuous time periodic, and therefore we have what's called the continuous time Fourier series. So input f of x is continuous and periodic, okay, and therefore the functions that are here also are continuous in x and periodic, right? So x is the variable, so sometimes we call it as time, sometimes x, and so on. And the variable and this is the complex coefficients that we use to weight these basis functions, right, to get the complete signal f of x, okay. And so the C of n, it will turn out to be nothing but discrete. Now it will be discrete and aperiodic, okay. So that is the basic idea of continuous time Fourier series. So in previous courses, when you did signals and systems and Fourier analysis, you would have first dealt with the Fourier series of continuous time periodic signals, okay. So similarly, if I have discrete signal, right, and periodic, right, so this I had made a mistake last class, so I have corrected it now. So this is discrete and periodic, right. So if it is discrete and periodic, then what it also implies is that the basis functions also will be discrete. That's why we have the variable n here, and they will also be periodic, okay. And it so happens then this should be not it should be a of k or c of k, both of them are same. I should again correct them, and this should be f of n. There are some mistakes that I made, but nevertheless the output also will be discrete and periodic, okay. So this is very important. Actually, this is what is practically used. So this will give rise to something called the discrete Fourier transform. Remember, when it's discrete, I can store it on a computer, right, because these are a set of numbers. Of course, I need something called quantization for finite precision, and because it is periodic, I just need to store one period, right, which is finite always. So I need to store only finite set of numbers because it's periodic both in time and in frequency, and therefore I can handle it on computers. In continuous time, there's no way that I can store all of the data on a computer, digital computer, right. So that is the basic idea. So discrete time Fourier series and its special case of that, which is called the DFT, is the most important thing. We'll deal with it later, okay. Now comes the other set of, so we talked about continuous time and discrete time, both of which are periodic. What if I had continuous time aperiodic signals, right, and there the summation will just come out to be an integration, right, and therefore these are useful for continuous time aperiodic signals, and the term we use is continuous time Fourier transform, okay. So here we are dealing with continuous time representations, okay, and if I have a discrete time representation of that, that is called the discrete time Fourier transform. So just like the first slide had discrete continuous time but periodic, here we are going to deal with continuous time. Input is always going to be continuous time aperiodic or discrete time aperiodic, okay. Sorry, let me just go back. So it's continuous time aperiodic or discrete time aperiodic. So whether it's continuous or discrete, that is the only thing that is going to change, okay. So the input can be x of t, which is continuous and aperiodic, or here it is x of n, which is discrete and aperiodic. Okay. So, this is the Fourier transform for the uh, continuous time aperiodic and discrete time aperiodic representations. Okay. So, these are things that we will encounter. This is actually called the synthesis part of it, that is sorry, analysis part of it. Here I am analyzing what frequencies are present. Okay. So, x of omega, in fact, if we should be a little more careful, we normally in our textbooks put the left hand side with a capital omega and the right hand side with e to the power of j omega. In fact, the left hand side we put j omega and so on, because this is a special case of something called the Laplace. Okay. And in the e to the power of j omega is a special case of something called the Z transform, which we will see next. Okay. So, but what is most important in all of this analysis is that we can do Fourier analysis on a digital computer, right, by using something called discrete Fourier transform. This is nothing but a special case of the discrete time Fourier series that we saw before. The advantage in this kind of representation, of course, apart from the quantization which you have to worry about, is both in the xn domain and in the xk domain. So, n and k are both discrete, right. So, they are samples, they are numbers that I can deal with, and they are only finite in both directions. K will also go from 0 to n minus 1, small n also will go from 0 to n minus 1. Okay. So, they are both finite in the time and frequency domain. So, this is the most commonly used transform, which is called the DFT, and there is a special algorithm, a special way in which we can do it very fast, and that is called the fast Fourier transform algorithm or the FFT algorithm. There are many variations. There is a Cooley-Tukey, the Sandy-Tukey, and so many other things, right? Decimation in time and decimation frequency. This DFT, the implementation, which is FFT, which is very fast, was actually first, the idea came out, Tukey came up with the idea, and he and Cooley actually designed the whole algorithm, and I was fortunate because Cooley taught me this entire course. Okay. So, as I said, there is signals, and we try to analyze signals. We can construct signals like how vectors from in some as a combination of basis functions and so on. Then there are systems, right? What are systems? Systems are something that take input some signal and manipulate it and may or may not give you a useful signal at the output. So, when we design systems, we try to extract something useful, right? But nature also is a signal, a system, right? So, when I am speaking and my mobile phone sends the message across to the base station, right? There is atmosphere that it goes through, right? That acts like a channel, right? So, there might be noise, there might be pressure variations, temperature variations, all of these affect the signal, right? And therefore, that whole channel acts like a system. The input is what you send here and the output is received at the base station, but in between, right, there is some channel, right, that takes it, or a telephone channel where we have the wire, right, the landline where we have the wire, that is the system, right, or even transduction, right. So, when I speak, right, that is picked up by the microphone. So, the microphone's input signal is the rarefactions and the output signal is the electrical variations of that, right. So, all of these are systems, okay. But in this course, we specifically will talk only about digital kind of systems, right, because we are dealing only with computers, and that is the more practical scenario where we are always going to be talking about. And so, we need a way to analyze these systems. You may have heard of something called the Laplace transform that is used for the continuous time systems. Here, we will only talk about the Z transform, which is the analog or the analogous thing to do for discrete time signals and discrete time systems. Okay. So, Z transform is basically looking very similar, if you look at it, to a Fourier transform. You can see Z, xn, z raised to the power of minus n. If I go back, you can see that there is very similarity between what I have done here, right, or even here if it does more. So, if you see x of omega is e to the power of minus I omega n. So, if I write this z as e to the power of minus z to the power of I, z equals e power I omega, then this will become z power minus n, right. And this looks very similar to the Z transform that I have, right, Z raised to the power of minus n xn, right. So, actually Z transform is a more general representation of the discrete time Fourier transform, okay. But we typically talk about Z transform when we are trying to design, analyze systems and so on, okay. And so, that is the perspective from which you should look at Z transforms, okay. So, what is a system? A system, as I said, is something that takes some input signal x of n, manipulates it and gives another signal y of n, right. It may just be an identity system, it can take xn and just output yn xn back, right. So, that is basically an identity system, or it can completely do something different and so on, right. So, some systems we design, and therefore, as humans we may want to do something useful out of it. Sometimes nature acts is the system, and therefore, it might do some corruption or something, right. And so, there are many things that we have to deal with. So, system is basically anything that takes input signal and gives you an output signal, okay. And typically, we talk about systems having certain properties. I am not going to go into much detail about these things. So, there is something called the property linearity property, the time invariance property, memoryless, so causality and stability, okay. These are all important, and I will only talk about a few of them, okay. One of the most important ideas is what we call as linearity, right. And the basic idea is that if I have signal x1 which passes through the system and I get an output y1 of n, and I pass a signal x2 through the system and I get a output y2, then if I add these two signals at the input, if it is a linear system, one of the properties is that the output also should be the addition of the corresponding outputs y1 and y2, okay. And then we have the other property, or the homogeneity property, or where we basically, if I multiply by a scalar, it can be a complex scalar, the output also should be multiplied by the same scalar, okay. That is called the linearity property. And then we have the time invariance property, which essentially means that if I give an input at a point and then I get an output, if I delay or advance the output, right, the input, the output also should be delayed or advanced by the same amount. That is the basic idea of time invariance, right. So, and if these two properties are there, right, and I will not go through the details, but if you remember that we need this linearity and time invariance, if these two are there, then okay, so there is this memoryless, which I will not talk about. Memory means does it depend on the future or past samples. So, in digital signal processing, memories can be in the future, because sometimes we can store data and look ahead also, okay. And therefore, it looks unnatural. Memory in our mind always means something in the past, but in a digital signal processing perspective, it could also be looking some samples in the future. That also means future memory, okay. So, that is one aspect. Memory or memoryless, or memoryless means only at that particular instant what happened determines the output, but memoryless means something in the past, something in the future. All of them are memory systems, okay. Similarly, causality is something that we do use a lot, and the basic idea here is that do I depend only on the past and the present values of the input to determine the output, okay. Those are generally said to be causal systems, and if I am also looking at something into the future, right, then it basically means that it is a non-causal system, okay. And as I said, causality is not a very important constraint in today's modern day signal processing, because we often buffer and keep some information and then start processing, right. So, it can have access to future samples also, okay. So, I was talking about and stability is very crudely put, that if my input is bounded, right, what do we mean by bounded? That it does not take it does not take very large values, it does not explode, right, it is finite valued in for all values of the input. Then we want the output also to be bounded, that it should not explode, okay. So, if my input is always finite and all the samples have finite values, then the output also should have at every sample, the output also should be bounded. That's a basic idea of stability. Okay, you don't want it to become large, even though my input is only a very small value. Suddenly, if it becomes large and becomes, explodes, then that is said to be an unstable system. Okay. So, I was saying before, and I repeat now, linearity and time invariance are two important properties that we often use, and to a large extent, these are not very unreasonable assumptions in many applications. At least these are quasi-stationary, so I can assume time invariance for reasonable periods of time during which I want to process it. So, if I assume linearity and time invariance, then there is a powerful idea that comes through, which is called the convolution. So, what it means is that if I pass an impulse, and I have not talked about an impulse, this is like a pilot signal, a sharp signal which occupies a very small period of time, right, and I observe the output, right, then I can actually get the output for any given input by this convolution operation. So, two things I need. I need to first get this idea of impulse, response to the impulse, which is called the impulse response. So, if the system is linear and time invariant, then I give the sharp small duration signal, okay, and I measure the output. This is the only measurement that I need to do. That's called the impulse response. Then you give me any arbitrary input x of n, then I can, without even actually passing it through the system, I can mathematically tell you what the output y of n will be by using this convolution sum. Okay. So, here I am talking about discrete time systems, because as I said, in our course we are always going to deal with digital and discrete time representations. So, this is called the convolution operation. So, the input x of n, and if I measure what is the response system to an impulse, and I measure, so I give an impulse here, and if this is linear and time invariant, I will get an output h of n. That is what is measured here, and then once I do this once, this is all I have to do once, then for any arbitrary input, the output is given by this convolution sum. Okay, that is the beauty of linear time invariant systems. Okay, so and when we talk about systems, one of the most often talked about term is in systems theory is this idea of filter, right. So, what does a filter mean? So, intuitively filter means it retains certain things and removes certain other things, right. So, we want to filter out dirt or something. When you have water, you put through something and water comes through and it removes all the solid particles and so on, right. So, filter basically is some way of separating out, right, some unwanted things from useful things, right. So, that system is one of the useful systems is this concept of filter, right, where I have x of n that may have unwanted, like water mixed with some solid particles, right, and I want to get the water back and remove the solid particles. I can pass through a filter and get only the pure water, right, after removing the solid particles and so on, right. And if we know that if it is LTI, then we can talk about something called the impulse response, and the output can be found by the convolution sum, correct. Now, what is the basic idea of filters, right? Just to give you an example why they may be useful. So, remember always we talk about time, and in our theory, as I said, we also are interested in something called the transform representation. So, what were the transform representations? We talked about the Fourier representations, right. So, we talked about Fourier analysis, or Fourier transform that took the time domain signal and went into the frequency domain representation, right. So, and as I said, I have told in the first class itself, the information content is the same, right. So, the same information is present, but sometimes it might be more visible or more easy to extract in the time domain, and sometimes more easy or more useful in the frequency domain. But the same signal, it is the same signal, right, but two different ways of looking at the same signal, right, like two different ways of looking at a coin. They still happen to be a 5 rupee coin, right. One side could be heads and the other side could be something else. It is the same coin, but each gives some different view of the same coin, right. So, in systems theory, we have the operation of convolution, and if you actually take the Fourier transform of this, surprisingly you will see that it turns out to be that the convolution in the frequency domain is nothing but the multiplication of the Fourier transform of x and the Fourier transform of h. Okay. So, this is a very important concept. Convolution in one domain always gives rise to something called multiplication in the other domain. This is again something that you would have seen in some course on signal processing or in signals and systems theory somewhere during the first part of the this course, right, in this program, right. And if you have not, please go back and refresh it, right, revise it. Okay. So, what is this, why are filters so important, right? So, for example, let me give you an idea, right. So, there are, if you look at a signal, right, that can be corrupted by noise. Okay. Now, if I am looking at the frequency, as I said, time is one way of looking at the signal, frequency is another way of looking at the signal. So, if I look at the signal in the frequency domain, this triangle, the big triangle is my signal, but because of noise there are some additional parts in the signal which are present, which I do not require. So, when I am speaking, somebody is saying whoosh, some sound is coming at the back, right. I want to remove that complete noise, and that noise, let us say, occupies this part of the signal, right. Now, intuitively you are interested in the main triangle here, that is in the low frequency part, and you want to remove these two triangles which are in the high frequency part, right. Intuitively you as an engineer know what to do, right. I have to just multiply this by 0, put 1 here and multiply by 0. That is essentially the filter that we desire, right. So, this is the spectrum of our desired filter, which passes the brown region with unity magnitude and all the other parts with 0 magnitude, right. That is basically when we design a system, right, we are going to say, make these specifications, it should be 0 in this region, it should be unity in this region, and so on, right. And if I do the job properly, the output will be only the desired signal, which is the big triangle. The two small noise triangles will be removed. And so, when I am talking, all the sound came, after you filter, it will be perfectly clear voice. Okay. So, there are many two broad classes. First of all, when you talk about filters, there are many ways that you can design filters. Here I am talking specifically about something called rational filters. I'll just make it a little more clearer. And there are basically two types of filters that we will deal with. One is called the finite impulse response filter, and the other is the infinite impulse response filter. Okay. So, what do I mean by rational? So, one of the important ways that we can describe systems, remember one way that I told you is here, right, where the system output depended on the input and some impulse response. Okay. This is one way of describing the system. Another way of describing the system, and there are large class of systems that can be represented this way, is where I can have an input output relationship of this form. So, the output at the nth sample is some linear combination of the output previous capital N samples and the input samples also. So, many systems can be described by this equation. This is basically what we call as a difference equation. You might have seen a differential equation which looks similar, right, yn and then dy by dx d squared a1 dy by dx plus a2 d squared y by dx squared plus a3, you can have a differential equation, right, and you might have solved such differential equations somewhere, right, either in high school or in the beginning parts of this course. So, there are large class of systems which can be, where the input and the output can be described by this particular difference equation. And if you take the Z transform, you will get basically polynomials. So, BR and AK, so these are polynomials in Z, and they are ratio of two polynomials. That is why we call them as a rational form, right, a ratio of two polynomials. These are a broad important class of systems. 95% of the time we deal with only such types of systems. Okay. Now, if this is a general description of a filter, right, which we often use in everyday signal processing. Now there are two special cases that we deal with. One is where all the AKs are 0, that is the output y of n depends only on the input. Okay. This is called finite impulse response filter. So, it does not depend on the past outputs. So, y of n only depends on the input, which is called the finite impulse response, and if it only depends on the current and past inputs, we say it is a causal filter. Okay. Another class of systems is where BR could be 0, I mean sorry, I should just say AK not 0, it is not necessary, again this is not true. BR can be 0 or may not be 0, but more importantly AK is not 0 here. Okay. So, the infinite impulse response depends on the past or the present or the future values of the output itself. Okay. So, therefore, we actually have FIR filters where AK is 0, so there is no past outputs coming into the picture, and IIR is where this also and this also exists, both exist. So, this is the general equation for an IIR system. Okay. And among the IIR, there is a special case where BR is 0, and that basically you can see leads to the linear prediction, right. Yn, if the right hand side is 0, Yn equals AK Yn minus k, that is a linear combination of the past outputs, which is essentially what we are talking about as linear prediction some last class, right. So, IIR filters, this is not a correct statement, should be that AK should not be 0, that is the basic idea. Okay. And so, remember I just now told you that if these are ratio of polynomials in the Z representation. So, now let us look at what is happening in the Z representation. Okay. In the Z representation, if we have it as a ratio of polynomials, right, I can root the polynomial, right, I can find the factors, right, I can root the polynomial. So, therefore, I can expand it in terms of the roots of the polynomial, correct. Now, if the value again this should be this is a representation in Z. So, this is also a representation in Z, this is a representation in Z, right. So, the values have to be basically, if I take the value Z takes a value Z1, it will go to 0, Z takes a value Z2, it will go to 0, right, or Z takes a value of P1, it will explode, it will become infinity, that is basically not good. So, let me take first the numerator factors, right. If Z takes a value of Z1, then it will go to 0. So, that is called a 0 of the polynomial, right, and therefore, the output also will be 0. So, if this value goes to Z equals Z1, it is always going to be 0. That is why the numerator polynomial, right, the numerator polynomial, the roots of which are called the zeros. If now Z takes the value of P1, then it explodes, right, it becomes infinity, right, and that is called a pole. That means, if I take a value close to this, the output will be very, very large, okay, and poles are nothing but the roots of the denominator polynomial. So, one has to be careful about poles, right. Zeros are at least something that I can handle, it will just go to 0, but poles are very, very important, right, because if I am close to a pole, then the output becomes infinity, right. And that is why when we design systems, we have to be careful about these poles, okay. And that is basically where we are talking about resonance frequencies, and you have to worry about when you design a bridge, right. There is a famous Tacoma Narrows Bridge, right, which was a fancy bridge built in the 1940s, and just a wind came, and then it sort of went into these oscillations and then broke the whole bridge, right. So, that is why when you design systems, you have to worry about what are the poles, where are the poles, and we have to make sure that we do not generate things that are frequencies that are close to these poles and so on, because otherwise the output can be disastrous. Okay. So, these are all some terms that I am using, because in speech signal processing we will refer to these zeros and poles. Okay. At least you should have an idea of what these things are. Okay. So, and let me just motivate why we did all of these things. Okay. So, if you remember, we are talking about systems, right, where input is x of n, output is y of n, right, and then this acts like a linear time invariant filter. Okay. Surprisingly, this is a very good model even for speech. Okay, so if my output S of n before quantization and discretization, but let us say S of t, that is the actual waveform that is coming, right? This filter is nothing but our mouth. Okay, it's a very good model. We can have a good representation for the whole thing that the mouth does. And x of n is the input excitation, that is the glottis, the vocal cords vibrating. Okay, so we will see that speech can be very well represented by a representation like this, a simple model where this h of n, we will see here, happens to be nothing but very simply this x of n and these y of n. So it is an IIR representation, and basically we will see that the poles and zeros are going to come into picture, and these poles and zeros are going to help characterize the different positions of the mouth, and therefore from that different sounds are produced. Okay, so that is the motivation why I was talking about this, because this is a typical model that is used in speech signal processing.